Okay, so if you see here, I was a bit lazy and I did not expand the tensors properly. So this is dou uj bar by dou xi, dou ui bar by dou xj, right? So I did not expand all the term, at least the 3 terms I should have expanded. Here I have set I equal to 1, 2, 3, the sum of 3, j remaining the same. I should have done that. So if I do this, basically this is only the 1 is expanded, but it's a sum of 3 terms. Summation in I, right? So it's 1 plus 2 plus 3. So I get the same nu t of dou uj bar by dou x2 and dou u2 bar by dou xj, and then plus I'll have nu t dou uj bar by dou x3 plus dou u3 bar by dou xj. The end result is the same. It's these 2 terms still vanish, the entire part, because here the u2 bar is 0 or your v velocity is 0. This is 0 here, and same here, u3 is 0, right? This. So I did not expand that term. Here, due to homogeneity, this entire term goes away, and here of course this is 0. So all the terms, all the 9 terms goes to 0, this entire part. Okay. So here Nirupam asked a very good question, that why like I gave the value here, experimental data m comes out to be 1.25 plus or minus 0.06 here, 0.0, okay, not much space, 0.06. So if you actually set this in, you are not getting 1.2, you are getting like 1.8 ish something. So that is true, the m value is correct. This C epsilon 2 is still used as 1.2, 1.92 in the standard K epsilon model, and the argument they place is they have also accommodated the free shear flows. So now this is, we are looking into, you know, decaying turbulence. So they are also looking into to accommodate for free turbulent shear flows. So this is used in standard K epsilon model. So if you set this value, you would get what is the value we got? The ratio, do you remember, Nirupam? This, if you substitute, the C epsilon 1 comes in a range, right? 1.8 plus or minus some value, 0.14 plus or minus 0.04, okay, plus or minus 0.4. This is what you get if you substitute. You don't get this, but in standard K epsilon model they recommend 1.92 value, saying that they have also considered the behavior for free shear flows, free turbulent shear flows, or free shear turbulent flows. So this 1.92 is used in the standard K epsilon model. This constants can slightly vary as you change a different K epsilon model. So what I am doing right now is for standard K epsilon, okay, how these 5 constants are appearing, right? Okay, so we'll go ahead with, we have other 3 more constants to look at, sigma k, sigma epsilon and C epsilon 1. We have looked into, sorry, this is C epsilon, oh yeah, correct, C epsilon 2, C epsilon 2, yes. So C epsilon 1 is still open, and sigma k and sigma epsilon, 2 more constants to look at, okay. So we have 3 more constants, sigma k, sigma epsilon and C epsilon 1. So sigma k and sigma epsilon is obtained by what used to be called computer optimization, and today of course you can use some other technique. So using computer optimization, sigma k is found to be 1 and sigma epsilon is found to be 1.3. Again, this is in standard K-epsilon model. All the values that I am giving out is on for the standard K-epsilon model. Okay. So now C epsilon 1 is the one that we have to look at. So to get C epsilon 1, I will go back to the logarithmic region of the flow again. Okay. So to get C mu, we looked into log law region, and then for C epsilon 2, we looked into a decaying turbulence. Now C epsilon 1 appears in the production rate of epsilon, right. So we will go back to the zone of the so called log law region. So for C epsilon 1, consider the log law region again, that is the inertial sublayer, log law region of a smooth turbulent boundary layer. Again, same considerations as before, that is statistically stationary, homogeneous along the two directions, homogeneous means statistical homogeneous, always statistically homogeneous along your x1 comma x3 direction, that is your in the xyz coordinate it is x and z. Okay, statistically homogeneous along x1 or x3 direction, and the flow is fully developed. Flow, which gives to your u2 bar equal to u3 bar equal to 0, that is v bar w bar, same consideration as before. So now we need C epsilon 1, and for that we will consider both the especially we consider the epsilon equation, right. To get the C epsilon 2, we took epsilon equation, we took a flow where some terms are negligible, we drop them and then obtained C epsilon 2. So we go back to epsilon, modeled epsilon equation. So modeled epsilon equation, this if I rewrite this, I would get dou epsilon by dou t plus uj bar dou epsilon by dou xj, the left hand side, and then of course the right hand part you would get your diffusion rate, right. So you have dou by dou xj of mu plus mu t by sigma epsilon, dou epsilon by dou xj, and the production rate of epsilon, which is C epsilon 1 epsilon by k pk minus C epsilon 2 epsilon square by k, or you can write epsilon by k here. Epsilon by k is the time scale that we introduced. So now if I consider all this, all the statistically stationary, statistically homogeneous, fully developed flow, all these considerations, I would get this term will go away. This upon expanding all the three will go away. Dou by dou x1, dou by dou x3 will go away, and in the other one it is u2 bar will go away. u2 bar, so this term also goes away due to all these considerations. So I would get 0 equal to, here dou by dou x1 and dou by dou x3 term goes away, again due to statistically homogeneous, right. So that is this part, dou by dou x1, dou by dou x3 of this average terms, though they go away. I get only dou by dou x2 term, which is dou by dou y of nu dou epsilon by dou y plus, I am just splitting this viscous and turbulent contribution to the transport, and then I get dou by dou y of nu t by sigma epsilon dou epsilon by dou y. Okay, so this dou by dou x or the dou by dou z terms, they go away here. So the viscous term and the turbulent diffusion rate plus I have this C epsilon 1 epsilon by k pk minus C epsilon 2 epsilon by k epsilon. Now in a log law region, and when we look into the transport terms, which term is dominant here to first order and which one will be negligible? You have this viscous, this is viscous diffusion, this is turbulent diffusion rate, and the pressure we dropped in the K model, and therefore it was dropped also in the epsilon model. Turbulent diffusion rate. So which is dominant in the log law region? The turbulent diffusion rate, right? The viscous is negligible, right? So this is negligible in the log law region. Viscous effects are not dominant. Viscous effects. Okay, so therefore the equation is, let's call this equation 1, which has 3 terms, one diffusion term, and then the production term and the destruction term. So now I would like to introduce scales here for the velocity and the length scale. I would like to introduce a scale to this equation, right? So we have, so the idea is that, the modeling idea is to introduce a turbulent scale in equation 1. Okay, so for the velocity scale, what do we use? For a turbulent velocity scale, I would like to use u star, that is the friction velocity. Okay, wall friction velocity. And I would like to introduce a turbulent length scale. A turbulent length scale, I use the mixing length, the kappa y. Okay, so I have where kappa is your one common constant. So I am essentially introducing turbulent scales here, u star and kappa y, and that I am going to introduce for the terms in equation 1, which is essentially epsilon. I need to introduce the scales to epsilon here, and then nu t of course, and then k and pk. These are the 4 terms that are there, and I need to introduce these scales inside these 4 terms. So first thing I will do is use the logarithmic region for the K model equation. So recall K model equation in the log law region. What do you get in the log law region? To first order, we saw that pk is balancing epsilon, all other terms are negligible, right? So pk equal to epsilon. To first order, right? So pk equal to epsilon, and what is epsilon dimensionally? Meter square per second cube. Okay, so this is dimensional arguments now, meter square by second cube. So placing dimensional arguments, using dimensional arguments, I get both for pk and epsilon, I can use u cube by L, which is u star cube by kappa y. So wherever I see pk and epsilon, I am going to use this. Let's call this equation 2. I am simply using some dimensional arguments here and introducing these two scales. Now pk and epsilon are done. Eddy viscosity and turbulence kinetic energy I need to introduce. So eddy viscosity, we already have the formula, right? So eddy viscosity nu t is c mu k square by epsilon, that is c mu I need for the k square, right? Yes. So from this I can obtain, well, before this I can say again dimensional arguments also for mu t. I can say here mu t is also a velocity and a length scale, meter square per second. So nu t I can simply introduce u star kappa y. Let's call this equation 3 here. So all I need is turbulence kinetic energy. For that I will use the relationship between eddy viscosity and k and epsilon, right? C mu k square epsilon. So I can use it to obtain the scales for k. So nu t is equal to c mu k square by epsilon. So I get k square is therefore nu t, which is u star kappa y, and then epsilon, which is u star cube by kappa y, and then divide by c mu. Okay, so some terms goes away, kappa y goes away, giving rise to essentially u star to the rise to 4 by c mu. So with this I get the expression k, I get this as c mu raised to minus half u star square. So this is equation 4. So now I can introduce equation 2, 3 and 4 in one. These scales or the equivalent of these scales for these 4 terms, epsilon, pk, nu t and k, inside one, to see what is the value for c epsilon 1.